Hello students, welcome to today's class. In today's class, we'll be talking about the design of compression members. So it's just a recap of the lecture 1 in this series, that is design of compression members. So in the design of compression members, broadly the compression members can be designed in two ways. The first way is the compression members can be designed as column sections. And the second way is the compression members can be designed as a struct members. Okay, so again in structs you have two types. One is the continuous struct, and the second one is the discontinuous struct. Continuous struct and the discontinuous struct. So for today's class, we'll be focusing on the design of compression members with respect to column. So again, in column, you have two different types of models of problems. One is the first model based on the analysis type, okay, and the second model is based on the design type. Similarly, in struct also, you have two different models of problems. One is the analysis based problems, and the second one is the design based problems. So let's stick our discussion to the design of compression members as a column sections. Okay, so here in analysis types of problems, what actually will be given? So let's look at analysis types of problems. So what actually will be given is they will provide a section, a specific section will be given in the question. Okay, so it can be an ISMB or ISHB or ISLB or ISWB. It can be anything, or ISJB. So a section will be provided in the question, and along with the section, they'll also give you the length of the member, that is L, okay, and they'll provide the end conditions of the member as well. So they will also specify the end conditions. That means whether both ends of the column are fixed, or one end is fixed and other end is free, or you can say the one end is fixed and the other end is hinged, or you can say both ends are hinged, or you can say one end is roller support and the other end is also the roller support. Likewise, you have different sections, right? Likewise, you have different end conditions. So these two parameters will be given in the question. That is, the section will be specified in the question, and also the length is also specified in the question. Now, what you will be asked to find out from these elements, right? You will be asked to find out the design compressive strength. Okay, you will be asked to find out the value of PD, which is the design compressive strength. So this is what they are going to ask you in the analysis types of problems. So you know the formula to find out the value of PD, that is PD equals to AE into FCD. So from this equation, you are going to get the value of PD. So however, we'll solve one type of problem which is based on analysis. So this is all about analysis. Now, whereas in the design-based problems, okay, whereas in the design-based problems of the column sections, so when you want to design a compression member as a column section, the step process will be followed in this way. So what they might provide in the question is they will provide the length of the member, that is L, and along with the length, they will also specify the end conditions of the member. They will also specify these end conditions, any one of these end conditions. If we have the table for these end conditions as well. So they will specify the end conditions. And along with this, they will also say that a particular section can carry how much amount of load. Suppose, say, for example, it can carry some X kilonewtons of load. So this load will also be specified. Now, what you have to do in this kind of problems are you are going to design the section. You are going to design the section. Now, how you are going to design the section? So the section can be designed in various ways. That is, initially you are going to find out the area required, and based on the area required value, you're going to select the section. Okay, select a section. And in the next step, what you're going to find out is you're going to find out the buckling class. That is, we have the buckling classes, like different buckling classes are available for us. We're going to find out the buckling classes, and then we are going to find out the section classification. That means you're going to classify the section in which way, right? The section classification can be done. And in the end, what you're going to find out is you're going to find out the value of PD, which is AE into FCD. Now you might have a question that what else we have done here. What you're going to do is in the first problem, that is in the analysis problem, they'll specify the section. Whereas in the design problem, you are going to find out the section based on the area value. Okay, you're going to find out the section based on the area value. Now, in here in the design problems, you need to check whether the section which you have selected here is safe or not. How will you check that one? So it can be checked in this way. That is, when you solve for PD equals to AE into FCD, the value of PD must be greater than the value of X, which is provided in the question. I said the value of X will be given in the question. Suppose, say for example, let us assume a load of 1000 kilonewtons is given in the question. Now, when you solve for PD value, you must get the value greater than 1000 kilonewtons. It is just an example. Okay, so then you can say it as a safe section. That means the section which you have selected here is considered as a safe section. Okay, anyways, we'll look into the both type of problems in the upcoming classes. And in now today's class, we'll be talking about the analysis based problems. So this is the problem which is based on analysis type. So the design of compression members as column, and you are going to do specifically the analysis model. So I have already said in here where the design of compression members can be done in two ways. One is based on column and the other one is based on struct. In today's class, we are sticking our discussion to column, and especially we are talking about the analysis types of problems. So this is the problem. So here a rolled steel beam ISHB 300 at the rate 58.8 kilogram per meter is used as a column. That means ISHB 300 is used as a column. So clearly it's a column type of question. And the column is fixed in position, but not in direction at both ends. So the column is, the end conditions of the column is also given. So determine the design compressive strength of section if the column length is, or if the length of the column is 5 meters. So as I was talking here, in the analysis type of problems, they will provide you the type of the section, that is, it can be ISMB, ISHB, and they will also specify the end conditions. And what they will ask you to find out is the design compressive strength, right? So that is what it is given here. So they have given the section, right, the type of the section, and they have also given you the end condition, that is column is fixed in position but not in direction at both ends, and you are asked to find out the compressive strength, that is the design compressive strength, when the length of the column is specified. So all the data is given in the question. Now let's solve for these values and find out the value of PD. So solution. So what we have to write initially is, let's write the given data. So given the length of the column, that is L equals to 5 meters. Okay, and the end conditions are also given, that is the end conditions are, so we have the column is fixed in position, that is the condition is fixed in position but not in direction at both ends. So let us keep this thing aside for time being and find, and I'll come back to this one after writing the given data. And they have also given you the type of the section, that is ISHB 300 at the rate 58.8 kilogram per meter. So ISHB represents, it's an I section. Remember, ISHP represents it's an I section. Usually for beams, we are going to use I sections only. So when you see Indian standard heavyweight beam, that means in the end, if you see B, that means it's an I section. Anyways, so this is the given data. Now let's write the sectional properties of ISHP 300. So the sectional properties of ISHP 300 at the rate 58.8 kilogram per meter, or so how will you get this? From steel tables book. So open the steel tables book and check down the sectional properties of ISHP 300. So the sectional properties are as like this. So the area is 7485 mm square. Okay, so this value is obtained from the code book, steel tables book, and the height equals to 300 mm, and the BF, that is width of the flange, equals to 250 mm, and the thickness of flange equals to 10.6 mm, and the thickness of web equals to 7.6 mm. And here you're also given with the radius of gyration, that is RZZ. So remember, RZZ and RXX, they both are same. So don't confuse between these two values. So the RZZ is given as 129.5 mm and RYY is given as 54.1 mm. So these are the sectional properties that are specified in the question. Now, before finding out, so what actually we have to find out? We have to find out PD value, that is AE into FCD. So this is what we have to find out. So in order to find out the PD value, you need two values, that is AE and FCD. So the AE value you know already from steel tables book, which is 7485. So AE equals to 7485 mm square. Now what we don't know the value of FCD. So in order to find out the value of FCD, you need to have in this way. So let's go in this way. In order to find out the value of FCD, you need to have the slenderness ratio value. Okay, you need to have the slenderness ratio value. How will you find out the slenderness ratio value? Which is KL by R minimum. Now here you need to find out the value of K, right? You need to find out the value of K. So how you are going to find out the value of K? You're going to find it from page number 45 of IS 800 2007. Anyways, I'll get back to that. So you need to find out the value of K. So once you find out the value of K, you also have to find out the value of R minimum, right? So R minimum, you have two values, that is RZZ and RYY. So let's look at which is the minimum value and then let's solve for this one. So let's proceed solving for this one. So the first step here is the value of K. So K equals 2, right? You need slenderness ratio value. Let's keep the heading as slenderness ratio. So how will you find out slenderness ratio? Lambda equals to KL by R minimum. So how will you find out the value of K? Now open steel tables book of page number 45. Okay, so page 45 of IS 800 2007. So let's look at the code book now. Now this is the page number 45 of IS 800 2007. So let's look at this. So what is this book saying? It is talking about the effective length of prismatic compression members. That means compression members are nothing but the column sections. Now, if you clearly observe this one, what you can find out here is you can find out the different end conditions are given, right? You can find out at one end, the boundary conditions are specified as at one end and at the other end. Now again at one end you have two conditions, right? You have the translation and you also have the rotation. Similarly, at the other end also you have the translation and rotation. Now you need to very clearly understand what are all these conditions talking about. Now let's go back to our problem and check down what is the condition that is specified in the question. So let's have a quick look into our problem. Now what is the condition that is specified? It is specified that the column is fixed in position but not in direction at both ends. That means you have a column section. Okay, so the column section is fixed in position. That means it will not move. So the column is fixed in position. Okay, now you have also given with one more condition, that is but not in direction at both the ends. So but not in direction at both the ends means it cannot move. Okay, the column is however fixed but it cannot move. What does it means is, it means it is a hinge connection. Okay, so that means when the column is fixed in position but not in direction, this means it's a hinge column. That means both ends of the column are hinged. Okay, now let's look at the table of IS 800-2007 and understand which property suits for here. Now here you can see the first one is talking about one end is fixed and the other end is free. The second one is talking about one end is hinged and the other end is roller. The third one is talking about both ends are hinged. And the fourth one is talking about one end is fixed and the other end is roller. Similarly, the fifth one is talking about one end is fixed and the other end is hinged. And the last one is talking about both ends are fixed. Now here in our question, the condition is given as the column is fixed in position but not in direction at both ends. What does it mean? It means it's a hinge connection. So for hinge connection, what is the value of effective length? So here you can see the effective length value. So the value of effective length is 1L. Okay, so therefore the value of K is 1. So that's how you're going to find out the value of K. So let's solve it here and write down the value of K. So therefore, from table 11, you can say it as from, I'll write the statement once again here. From table 11 of IS 800-2007, from table 11 of IS 800-2007, that is in page number 45. Okay, so that is in page number 45, K equals to 1. Okay, why? The both ends are hinged. Okay, when the both ends are hinged, then it is the value of K is 1. So therefore, KL equals to 1 into L. What is the length that is given in the question? It is 5 meters. You can see here, it is 5 meters. So 1 into 5 meters, I am converting into mm, which will be 5000 mm. So we have found out the value of K also, or KL as well. Now, in the second step, what you're going to find out is you're going to find out the buckling class. Okay, you're going to find out the buckling class. What does it mean? So any section, whatever the type of section, it can be an I section, channel section, of angle section, it can be any section. The sections can bend along two axes. One is along ZZ axis and the other one is along YY axis. Any sections can bend along two axes. One is ZZ axis and the other one is YY axis. Based on the bending phenomena of the axis, that is based on ZZ and YY axis, you have 4 buckling classes: buckling class A, buckling class B, and buckling class C and D. Now you need to identify which buckling class our section belongs to. Okay, now how will you find out this one? So for this, in order to find out the buckling class, you need to refer table 10 of IS 800-2007. So which is there in page number 44. So let's go back to the page number 44 of table 10 and look at which buckling class our section belongs to. Remember, our section is an I section, because we are clearly know it's an ISHP. ISHP represents it's a I section. So let's look at which buckling class it belongs to. So here you can see the table 10, which talks about the buckling class of cross sections, right? Now here you have this table, which is the cross section, its limits, and the buckling class about which axis. That means we have two axes. One is ZZ axis and YY axis. Remember, ZZ axis is also called as XX axis and the buckling class type. Now here, if you clearly observe this table, you have the buckling classes for different cross sections. That is, the first one is rolled steel I sections, and the second one is welded I sections, and the third one is hollow sections, and the fourth one is welded box sections, and the other one is for channel sections or angle sections or T sections and solid sections, and the extreme last one is for built up section. Now we know from our problem belongs to I section, right? Rolled steel I section. Now in rolled steel I section, you have again two types. One is rolled I section and the other one is welded I section. Now in our problem, they did not talk about whether it's a bolted connection or a welded connection. So if nothing is specified, take it as rolled steel I sections, which is going to be bolted. If it is clearly specified in the question that it's a section is a welded section, then only you have to go for this condition. Since nothing is specified about the type of the connection, we are going to assume it as a rolled steel I section, which is going to be bolted. Now, here what you have to check down is the limits you have to concentrate. So when you check the limits, you are given with two conditions. One is h by bf greater than 1.2 and the other one is h by bf less than 1.2. So these are the two cases which are given. So h by bf greater than 1.2 and h by bf less than or equals to 1.2, right? You can check down very carefully here. Now in h by bf greater than 1.2, you are given with when the thickness of the flange, that is TF, it is TF, when the thickness of the flange is less than or equals to 40 mm and the thickness of the flange lies in between the 40 and 100 mm. So lies in between 40 and 100 mm, right? So similarly, you are given with when h by bf less than or equals to 1.2, you have the thickness of the flange less than 1.2, sorry, less than or equals to 100 mm, and the other condition is greater than 100 mm. So first, let's check down whether the h by bf value is greater than 1.2 or less than 1.2. So once we check, then we come for these conditions. Okay, that is TF conditions. So let's quickly solve for that one. So what we are going to do, we are going to do the h by bf conditions. Okay, from table 10 of IS 800-2007, you can refer page number 44. The section is rolled I section. Rolled I section. We have seen this rolled I section. So for rolled I sections, in order to classify which buckling class it belongs to, okay, we have to check down h by bf value. What is the h value? It is height of the section, which is 300 mm, and bf is 250 mm. So h by bf is 300 by 250. So if you solve for this one, it is 1.2. Okay. Now, again, let's go back to the table and find out whether which condition is going to get clearly solved here. So you can check down here. So the h by bf is greater than 1.2 and h by bf less than or equals to 1.2. Now, what is the value of h by bf which we have got? It is 1.2. The value which we have obtained is 1.2. So therefore, our category belongs to this one, the second class. Okay, the h by bf value is less than or equals to 1.2. So that is clear for us. Here it is the h by bf value is less than or equals to 1.2. Since our h by bf value is equals to 1.2, we are taking the second condition. Now in second condition, again you have two more conditions. One is when thickness of the flange is less than or equals to 100 mm, and when the thickness of the flange is greater than 100 mm. Let's find out this also, whether the thickness of the flange is less than or equals to 100 or greater than or equals to 100. So let's find out. So it is less than or equals to 1.2. And the thickness of the flange, what is the thickness of the flange? It is 10.6 mm. So you can see it is 10.6 mm. So the thickness of the flange is 10.6 mm, which is less than 100, right? So let's look at the table again and check down which buckling class it will. So the thickness of the section, thickness of the flange is less than or equals to 100 mm. Now, in this condition, again, you are given with two conditions. One is ZZ and YY. So along ZZ, it belongs to buckling class B, and along YY, it belongs to buckling class C. That's what they have specified. So along ZZ, it belongs to buckling class B, and along YY, it belongs to buckling class C. Now we need to know which buckling class it belongs to. So let's write down this statement. Along ZZ, it belongs to buckling class B, and along YY, it belongs to buckling class C. So the section belongs to buckling class B. Okay, the section belongs to buckling class B along ZZ axis, and the same section belongs to buckling class C along YY axis, right? That is what we are talking. The section belongs to buckling class B along ZZ axis and buckling class C along YY axis. Now, you don't have two buckling classes for a same section. You will have either B or C. It is not that both B and C will be there. It can be only one. Either B will be there or C will be there. Now, how will you find out this one? Now here, in order to check which buckling class it belongs to, you need to note one condition. What is that condition is, make sure of noting this one, that is note. Remember, buckling always happens about minor axis. So remember, buckling always happens about minor axis. Now, what is the minor axis? You have the ZZ axis and you also have the YY axis. Now, how will you specify which axis is the minor axis and which axis is the major axis? Now, how will you find out that one is, you have the values of RZZ and you also have the value of RYY. So what is the value of RZZ? It is 129.5 mm and RYY is 54.1 mm. So RZZ equals to 129.5 mm, 129.5 mm, and RYY is 54.1 mm, 54.1 mm. So what we talked, buckling always happens about minor axis. Now, which is the minor value here? Is it 129.5 or 54.1? It is 54.1. So therefore, since the buckling class, the minor axis is, therefore, the minor axis is YY, right? Because you have the least value of R along YY axis. So the least value is 54.1. So therefore, the section belongs to, okay, so along which one it belongs to? It belongs to B or C. So along C, along YY axis, it belongs to buckling class C. The section belongs to buckling class C. And this is how you have to identify which section or which buckling class it belongs to. Now from this, you can find out the value of lambda. Therefore, lambda equals to KL by R minimum. So the value of KL is 5000, right? We have solved it here, 5000. So 5000 upon what is R minimum, that is least radius of gyration. We found the buckling class is along YY axis and it belongs to C. So therefore RYY value, that is minor axis value, is 54.1 mm. So if you solve for this one, you're going to get the answer as 92.42. Okay, 92.42. Now here it should satisfy a condition. So in order to satisfy a condition, this value must be less than 180. Now how will you get this 180? So this 180 value, you should get it from table 3 of IS 800 2007. So if you refer table 3 IS of IS 800 2007, especially point 1, you'll be getting this one. So let's quickly look into that value. So this is table 3 of IS 800 2007, which is there in page number 20. Now here you have the different maximum effective slenderness ratio values, that is KL by R values. You can see the KL by R condition. So you have the 6 different conditions, right? You have the 6 different conditions. And for each condition, you are given with one slenderness ratio value, which is the maximum value. That means the slenderness ratio which you have calculated must not be greater than these values. Now, here the member type, you are given with 6 different conditions. Now, our section belongs to a member carrying compressive load. We know it's a compression member. So a member is carrying the compressive load because we are designing the compressive members. So resulting from dead loads and imposed loads. So what is the maximum slenderness ratio value? It is 180. Okay, so when a member is carrying the compressive load, the maximum slenderness ratio value, that is lambda value, should not be greater than 180. So let's look at this one, whether the value which we have obtained while solving, is it greater than 180 or less than 180? Let's look into that one. So here we have got the value less than 180. Therefore, safe, right? Since it is satisfying the condition, it is safe. Now what we have to find out, we have to find out the value of FCD, right? I was telling you, in order to find out the value of FCD, you need to have lambda value. So we found out the lambda value here, right? Now the next process is to find out the FCD value. Now how will you find out this FCD value? So here you have to focus on the conditions. So how will you find it? So we know the section belongs to buckling class C, right? We know this one, it belongs to buckling class C, right? Just give me a minute, I'll erase all the parts and then we check back. Yeah, fine. So the section belongs to buckling class C. Now if you open the design compressive strength or design compressive stress values, that is the table values, you have tables 9A, table 9A, 9B, 9C, and 9D. So A talks about buckling class A, and 9B talks about buckling class B, 9C talks about buckling class D, and 9D talks about buckling class D. So each table talks about buckling class A, buckling class B, buckling class C, and buckling class D. So now our section belongs to buckling class C. So for buckling class C, you are going to refer table 9C. Okay, you are going to refer table 9C in order to find out the value of FCD. How will you find out? Let's check them. So from table 9C of IS 800 2007, okay, from table 9C of IS 800-2007, let's look at what this table consists of. Yeah, so this is the table 9C, which talks about the design compressive stress, that is FCD value, the design compressive stress value, which is FCD for column buckling class C. Okay, for FCD for column buckling class C. So let's look at the values here. So along x-axis, you are given with different values of yield stress. Okay, starting from 200 to up to 540, right? 200 to 540, right? Now on y-axis, you are given with KL by R values. So you have different KL by R values starting from 10 up to 250, starting from 10 up to 250, right? Now, what is KL by R? It is actually lambda, which is the slenderness ratio. Now, what is the slenderness ratio which we have obtained? It was 92.42. Now, let's find out the value of FCD, okay, when lambda equals to 92.42, right? So all these values, right, this entire values are the FCD values. Remember, all these are FCD values. Now we need to find out from this table, we need to find out what is our FCD value when lambda equals to 92.42. Let's check down this. Always remember, we are going to take the steel value, that is yield stress value, as Fy as 250 megapascals. So what is the lambda value which we have got? We have got 92.42. But here, if you check down, you have the value of FCD, right, when it is 90, right? When it is 90, you have the value as 121. And when it is 100, you have the value as 107. But you don't have the value for 92.42. So the 92.42 lies in between 90 and 100, right? So you know 92.42 lies in between 90 and 100. So we have to interpolate between these four values and obtain the value of FCD when lambda equals to 92.42. Okay, so you have to obtain the value of FCD when lambda equals to 92.42. So let's quickly write down when KL by R, it is this one, when KL by R is 90, the value of FCD for 250 steel is 121 and for 100 it is 107. Let's quickly write these values and start for the interpolation process. So here, so from table 9C of IS 800-2007, what we need to know, we need to have the value for 92.42 when FCD value has to be found out. Let us consider this as X, okay, or you can make it as question mark. So we don't know when lambda equals to 92.42, what is the value of FCD? So we know 92.42 lies in between 90, where when lambda equals to 90, the value of FCD is 121. We have got that value. And when lambda equals to 100, the value of FCD is 107. So you have to do the interpolation process. So by interpolation, so if you want to know the interpolation process, you can check down the very first video of this lecture series of design of compression members. So after interpolating, the value of FCD when lambda equals to 92.42 is obtained as 117.61 newtons per mm square. So why I'm taking newtons per mm square? Because all the values of FCD in table 9C, or for that matter, for table 9A, 9B, 9C, and 9D, they will be in newtons per mm square only, or megapascals. Anything is same. So we got FCD value also. So what we need to find out the PD value. So therefore, PD, that is a third step you can see. So therefore, the design compressive strength, you can make it as the design compressive strength, that is PD equals to AE into FCD. So we know the value of AE, which is the area of the section, that is 7485, and FCD value also we know, which is 117.61. So if you solve for this one, it is 880325 newtons. So let's convert this into newtons, kilonewtons. It will be 880.325 kilonewtons. Now, how will you find out this section? I mean, the design compressive strength of ISHP 300 is 880.3 kilonewtons or 0.325 kilonewtons. So this is how you can find out the design compressive strength in the analysis types of problems. So let's quickly recap what we have done. So we have done, since we need to find out the value of PD, that is AE into FCD value. So this one. So this one we have to find out, AE into FCD value. AE is obtained from the steel tables book for the given section. And the slenderness ratio, in order to find out the FCD value, we need to find out the slenderness ratio. And here you need to get the value of K from table 11. Okay. And then you have to find out the buckling class. Okay. So how you are going to find out the buckling class? You're going to refer table 10 and identify the type of section. So since our section is an I section, it belongs to different types of buckling classes. So in order to find out which buckling class it belongs to, you need to find out these conditions, that is H by BF and TF. So since H by BF is less than or equals to 1.2 and TF is less than 100, it belongs to buckling class B along ZZ axis and the buckling class C along YY axis. Now, in order to find out which buckling class it belongs, specifically, it can belong either to buckling class B or buckling class C. So we need to identify which buckling class it belongs. So in order to identify that, we got to know that buckling always happens about minor axis. So whichever is having the least value of R, for that you are going to take. So therefore, the minor axis is YY axis because RYY is having the least value. So therefore, it belongs to buckling class C. So from there, you can find out the value of lambda, and it should satisfy the conditions which are specified in table 3 of IS 800. And from then, you are going to refer table 9C because our section belongs to buckling class C. Right? Now, by interpolation, you're going to find out the value of FCD, and from then on, you can find out the value of PD, that is AE into FCD. So this is how you can solve the problem. So you can solve, I'll give the 2 more problems. You can keep that problems as your assignment work, or you can solve just to ensure whether you have got the process or not. So the problems are 2, 3, as you see on the screen. So solve these 2 problems as your understanding purpose. And in the next class, we'll be solving the design of compression members, which is specifically related to column sections, right? So these 3 problems, that is the solved example, which is this one, and the second and third problems are for your assignment, which are based on analysis type. In the next class, we'll talk about the same models of problems. How will you design? Okay, thank you.